incline, 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 incline,
giant, 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 giant,
oriented, oriented, trove, trove. Trove, This is Wix Studio.
An analysis of algorithms. I imagine many of you are already clear on your reasons for taking this course, but let me begin by justifying the course's existence and giving you several different motivations for learning about algorithms. So what is an algorithm? Well, we're not going to be needing a precise definition in this course, but essentially an algorithm is a well-defined set of rules, a recipe in effect, for solving some kind of computational problem. So for example, maybe you're given a bunch of numbers and you want to rearrange them into sorted order. Maybe you're given a road network with an origin and a destination and you want to compute the shortest path from point A to point B. Maybe you're given a bunch of tasks with deadlines and you want to know whether or not it's feasible to accomplish all of those tasks by the respective deadlines. So why study algorithms? Well, first of all, understanding the field of algorithms and also the related field of data structures is crucial for doing serious work in pretty much any other branch of computer science. That's the precise reason why here at Stanford University, this is the course that's required for all of the degrees that the computer science department grants. Be it a bachelor's, a master's, or a PhD degree, we insist that you have mastery of the field of algorithms. So what are some examples of uses in the rest of computer science? Well, if you're doing routing in a communication network, that piggybacks on classical shortest path algorithms. The effectiveness of public key cryptography really rests on that of number theoretic algorithms. In, say, computer graphics, you need the computational primitives that are supplied by the study of geometric algorithms. Database indices rely on balanced search tree data structures, as covered in this course. And computational biology uses dynamic programming algorithms to measure the similarity among genomes. And the list goes on and on. A second reason to study algorithms is that they play a key role in modern technological innovation. Obviously, I could give any number of examples here. Let me just state one super obvious one, which is that search engines use a tapestry of algorithms to efficiently compute the relevance of various web pages. The most famous such algorithm, which you may have heard of, is the PageRank algorithm in use by Google. Indeed, in a December 2010 report to the United States White House, the President's Council of Advisors on Science and Technology argued that, in many areas, performance gains due to improvements in algorithms have vastly exceeded even the dramatic performance gains due to increased processor speed, as you'd be familiar with in the form of Moore's Law. Third, although this is getting significantly outside the scope of this course, algorithms are increasingly being used to provide a novel lens on processes outside of computer science and technology. For example, the study of quantum computation has provided a new and computational viewpoint on quantum mechanics. Price fluctuations in economic markets can be fruitfully viewed as an algorithmic process, and even evolution can be usefully thought of as a surprisingly effective search algorithm. The last two reasons I'm going to give you might sound a little flippant, but I think there's more than a grain of truth to both of them. Now, I don't know about you, but back when I was a student, my favorite classes were always challenging classes, but after I struggled through them, I somehow felt like I had a few more IQ points than when I started. So I hope this course provides a similar experience for many of you, that on the one hand, it's a bit of a struggle, you find the concepts challenging, but perhaps you feel just a tinge smarter after we're done. Finally, I hope that by the end of the course, a constant fraction of you will agree with me that designing and analyzing algorithms is simply fun. It's an endeavor that requires a rare blend of creativity and precision, and it can certainly be frustrating at times, but even more than that, it is addictive. So let's now descend from these lofty generalities and get much more concrete. And also, let's remember that we've all been learning and using algorithms since we were little kids. So once upon a time, in roughly third grade or so, you learned how to multiply two numbers. Now, you probably weren't thinking in these terms at the time, but multiplying two numbers is certainly a well-defined computational problem, and that procedure you learned back in third grade or so is indeed an algorithm. So let's just make that a little bit more precise. In this computational problem, we're given as input two numbers, let's say with n digits. And to make things interesting, why don't you think about n as being really quite large, say in the thousands. Maybe we're implementing an algorithm that's going to be used in a cryptography application where you need to keep track of really quite large numbers. So if we call the two input numbers x and y, the problem is simply to compute their product, x times y. So a quick digression. I'll certainly be the first to admit that my handwriting is not the greatest. I got a C in penmanship back in elementary. Two numbers, let's just call a step the addition or multiplication of two single-digit numbers. So let's review the integer multiplication algorithm that we learned back in grade school just by working through a concrete example. Specifically, let's think of n equal 4, so let's look at two 4-digit numbers. Let's say 5, 6, 7, 8, and 1, 2, 3, 4. Now, as you'll recall, the procedure we learned way back when was just to take each digit of the bottom number and multiply it by each of the top numbers, and then to take each of those n partial products and add them up. So for example, you start with the 4, you multiply it by 8, you get 32, carry the 3, 4 times 7 is 28, add the 3, you get 1, carry the 3, and so on. So that gives you this first partial product, 22, 7, 12. Then you do a shift, so you effectively put a 0 in this final digit, and you repeat that procedure using so on, using the text you sit in, and digit number signs, and so the part of over n.
All right, so binary search is an algorithm we can use to find an element inside of an array. Unlike linear search, it requires a special condition be met beforehand, but it's so much more efficient if that condition is in fact met. So what's the idea here? It's divide and conquer. We want to reduce the size of the search area by half each time in order to find a target number. This is where that condition comes into play, though. We can only leverage the power of eliminating half of the elements without even looking at them if the array is sorted. If it's a complete mix-up, we can't just out of hand discard half of the elements because we don't know what we're discarding. But if the array is sorted, we can do that because we know that everything to the left of where we currently are must be lower than the value we're currently at, and everything to the right of where we are must be greater than the value we're currently looking at. So what's the pseudocode steps for binary search? You repeat this process until the array, or as we proceed through, sub-arrays, smaller pieces of the original array, is of size 0. Calculate the midpoint of the current subarray. If the value you're looking for is in that element of the array, stop, you found it, that's great. Otherwise, if the target is less than what's at the middle, so if the value we're looking for is lower than what we see, repeat this process again, but change the endpoint instead of being the original complete full array to be just to the left of where we just looked. We knew that the middle was too high, or the target was less than the middle, and so it must exist, if it exists at all in the array, somewhere to the left of the midpoint. And so we'll set the array location just to the left of the midpoint as the new endpoint. Conversely, if the target is greater than what's at the middle, we do the exact same process, but instead we change the start point to be just to the right of the midpoint we just calculated, and then we begin the process again. Let's visualize this, okay? So there's a lot going on here, but here's an array of 15 elements, and we're gonna be keeping track of a lot more stuff this time. So in linear search, we were just caring about a target, but this time we want to care about where are we starting to look, where are we stopping looking, and what's at the midpoint of the current array. So here we go with binary search. We're pretty much good to go, right? I'm just going to put down below here a set of indices. This is basically just what element of the array we're talking about. With linear search, we care in as much as we need to know how many elements we're iterating over, but we don't actually care what element we're currently looking at. In binary search, we do, and so those are just there as a little guide. So we can start, right? Well, not quite. Remember what I said about binary search? We can't do it on an unsorted array, or else we're not guaranteeing that the certain elements or values aren't being accidentally discarded when we just decide to ignore half of the array. So step one with binary search is you must have a sorted array, and you can use any of the sorting algorithms we've talked about to get you to that position. So now we're in a position where we can perform binary search. So let's repeat the process step by step and keep track of what's happening as we go. So the first thing we need to do is calculate the midpoint of the current array. We'll say, first of all, we're looking for the value 19. We're trying to find the number 19. The first element of this array is located at index 0, and the last element of this array is located at index 14. And so we'll call those start and end. So we calculate the midpoint by adding 0 plus 14 divided by 2, pretty straightforward midpoint, and we can say that the midpoint is now 7. So is 15 what we're looking for? No, it's not. We're looking for 19, but we know that 19 is greater than what we found at the middle. So what we can do is change the start point to be just to the right of the midpoint and repeat the process again. And when we do that, we now say the new start point is array location 8. What we've effectively done is ignored everything to the left of 15. We've eliminated half of the problem, and now instead of having to search over 15 elements in our array, we only have to search over 7. So 8 is the new start point, 14 is still the end point, and now we go over this again. We calculate the new midpoint. 8 plus 14 is 22, divided by 2 is 11. Is this what we're looking for? No, it's not. We're looking for a value that's less than what we just found. So we're going to repeat the process again. We're going to change the end point to be just to the left of the midpoint. So the new end point becomes 10. And now that's the only part of the array we have to sort through. So we have now eliminated 12 of the 15 elements. We know that if 19 exists in the array, it must exist somewhere between element number 8 and element number 10. So we calculate the new midpoint again. 8 plus 10 is 18, divided by 2 is 9. And in this case, look, the target is at the middle. We found exactly what we were looking for. We can stop. We've successfully completed a binary search. All right, so we know this algorithm works if the target is somewhere inside of the array. Does this algorithm work if the target is not in the array? Well, let's start it again, and this time let's look for the element 16, which visually we can see does not exist anywhere in the array. The start point is again 0. The end point is again 14. Those are the indices of the first and last elements of the complete array. And we'll go through the process we just went through again, trying to find 16, even though visually we can already tell that it's not going to be there. We just want to make sure that this algorithm will in fact still work in some way, and not just leave us stuck in an infinite loop. So what's the step first? Calculate the midpoint of the current array. What's the midpoint of the current array? Well, it's 7, right? 14 plus 0 divided by 2 is 7. Is 15 what we're looking for? No, it's pretty close, but we're looking for a value slightly bigger than that. So we know that it's going to be nowhere to the left of 15. The target is greater than what's in the midpoint, and so we set the new start point to be just to the right of the middle. The midpoint is currently 7, so let's say the new start point is 8. And what we've effectively done again is ignored the entire left half of the array. Now we repeat the process one more time. Calculate the new midpoint. 8 plus 14 is 22. Divided by 2 is 11. Is 23 what we're looking for? Unfortunately, no. We're looking for a value that is less than 23. And so in this case, we're going to change the end point to be just to the left of the current midpoint. The current midpoint is 11. And so we'll set the new end point for the next time we go through this process to 10. Again, we go through the process again. Calculate the midpoint. 8 plus 10 divided by 2 is 9. Is 19 what we're looking for? Unfortunately, no, we're still looking for a number less than that. So we'll change the end point this time to be just to the left of the midpoint. The midpoint is currently 9, so the end point will be 8. And now we're just looking at a single element array. What's the midpoint of this array? Well, it starts at 8, it ends at 8. The midpoint is 8. Is that what we're looking for? Are we looking for 17? No, we're looking for 16, so if it exists in the array, it must exist somewhere to the left of where we currently are. So what we're going to do? Well, we'll set the end point to be just to the left of the current midpoint. So we'll change the end point to 7. Do you see what just happened here, though? Look up here now. Start is now greater than end. Effectively, the two ends of our array have crossed. And the start point is now after the end point. Well, that doesn't make any sense, right? So now what we can say is we have a subarray of size 0. And once we've gotten to this point, we can now guarantee that the element 16 does not exist in the array because the start point and end point have crossed, and so it's not there. Now notice that this is slightly different than the start point and end point being the same. If we had been looking for 17, it would have been in the array, and the start point and end point of that last iteration before those points crossed, we would have found 17 there. It's only when they cross that we can guarantee that the element does not exist in the array. So this took a lot fewer steps than linear search. In the worst case scenario, we had to split up a list of n elements repeatedly in half to find the target, either because the target element will be somewhere in the last division, or it doesn't exist at all. So in the worst case, we have to split up the array, do you know? Log of n times. We have to cut the problem in half a certain number of times. That number of times is log n. What's the best case scenario? Well, the first time we calculate the midpoint, we find what we're looking for. In all of the previous examples on binary search we've just gone over, if we had been looking for the element 15, we would have found that immediately. That was at the very beginning. That was the midpoint of the first attempt at a split of a division in binary search. And so in the worst case, binary search runs in log n, which is substantially better than linear search in the worst case. In the best case, binary search runs in omega of 1. So binary search is a lot better than linear search, but you have to deal with the process of sorting your array first before you can leverage the power of binary search. I'm Doug Lloyd. This is CS50.
All right, team, we're transitioning.
In some past videos, I've talked about binary search trees and how to put them together. However, I took a data set that was very well structured, and so the tree was nice and balanced. And then in some of our other videos, we went over red-black trees and how to balance a tree that wasn't really structured the way you'd want a red-black tree to be structured. In this video, I'm going to show you how you can take an array and how you create or construct a binary search tree based on the elements of that array in their original order. So you can see on the right-hand side here, we have an array with elements 5, 7, 1, 15, 9, 2, 14, 8, 7, and 3. And so if we're going to create a binary search tree with this array, they have to actually go in order. And so I'm going to show you how that works. So the first element in our array is going to be 5. And so it's nice, easy. We create 5 and put it inside of at the root node. The next one we're going to use is going to be 7, and because 7 is greater than 5, it'll do that comparison, and then it'll put 7 on the right-hand side right next to 5. After that, we have a 1. 1 is less than 5, so it goes to the left, and right here we have a very nice basic tree structure. We have our root node, we have 1 being the item or the node to the left, 7 to the right. So far everything is normal. Now we're going to add 15. 15 is greater than 5, it's greater than 7, so it needs to go all the way to the right. Now I'm just going to start adding some more in order in the array. So we'll go 5, 7, 15. Now 9 is less than 15, and so we put it there on the left. Now, if you are familiar with red-black trees or some of these more self-balancing trees, you would know that this is not the way this would have been constructed. It would have rebalanced itself and would have swapped out the 9 right here, so the 9 would be connected to the 5, the 7 would be on the left-hand side, 15 on the right-hand side. However, this is just a regular binary search tree, so we have to treat it as such, and we have to add the elements in order. And this is the reason why people created things like red-black trees, was because, as you'll see here in a minute, this tree is going to look pretty odd in a short period of time. So next element is 2. 2 is less than 5, so we know it goes to the left. It's greater than 1, so we'll get pulled over into the right. Then we're going to add 14. It's greater than 5, greater than 7, but less than 15, so it's going to move to the left. And it's greater than 9, so you'll see that moves all the way to the bottom of our binary search tree. So we have 14, we have just 3 elements left. We have 8. It's going to traverse the tree. We see that it's greater than 7, but less than 15, and less than 9. And our second to last one is 7. Now that 7 is an interesting one, because you can see that it is greater than 5, it gets 9. All that happens is what a visual representation of the tree would look like. So it is a 3, and the representation of the tree would look like. So you can see it's not balanced, however, it is properly structured. If you were to run a search on this, so say that we wanted to find 8. So if we want to find 8, it'll go to 5, 7, 15. It's less than 15, so it knows to look to the left. It's less than 9, and there it is. That it found the element. So this is how you construct a binary search tree given an array.
Woo! Mm.
In computer science, data structures are ways to store and organize data so it can be used efficiently. Knowing about data structures is important because picking the right one can dramatically affect the performance of a program. Let's look at 2 of the simplest data structures, stacks and queues. First, stacks. The word stack in computer science is used a lot like it is in English, so let's think of a stack of books. If you want to add a book to the stack, you'll add it to the top. And if you want to get a book from the stack, you'll start from the top as well and remove elements. It's cumbersome to access a book in the middle of the stack, so we generally avoid that. A stack has a top and a bottom, and we can add and remove only from the top. In computer science, we tend to talk about pushing elements onto the top of a stack for adding, and popping elements from the top of a stack for removing. So a stack is a data structure in which elements are sorted by insertion order. The last element that you put in is the first one that's going to come out. Elements have no index, so we can't access them in the middle of the stack. We can only add to the top and remove from the top, pushing and popping. Stacks are useful in contexts in which we want to reverse the order of elements. For example, think about the undo button in a lot of applications. The application stores activities performed in a stack. And so when you press the undo button, the activity that's undone is the last one that was performed. Now let's look at queues. The word queue is not used in American English very often, but in British English it means a single file line. So let's think about a line at a movie theater. So somebody starts the line and additional people may join after the first person. And the first person to get help will be the first person who joined the line. So queues have a front and a back, and we can add elements to a queue only from the back, and we can remove elements only from the front. In computer science, we might talk about adding as enqueuing and removing as dequeuing. Just like in stacks, elements in queues don't have indexes, so we can't access them directly. Again, think about the movie theater line example. The person working at the theater can't just ask the person in the red shirt to come and be helped. The patrons get helped in order. So a queue is a data structure in which, just like stacks, elements are sorted by insertion order. However, in queues, the first element that you put in is the first one that comes out. Again, elements have no indexes, so we can't access an element in the middle of a queue. We can only add to the back and remove from the front. Queues are useful in contexts when we're managing resources. For example, think of a print queue. If we have many people in an office sending jobs to the same printer, the first person who sends a job to the printer gets their job first. Similarly, if we have a website and several people are accessing that website, the first person who tries to access it is the first person who gets the page back.
Keeping it fresh like plastic wrap, that's me. Yeah, that's me.
In this lesson, we are going to talk about binary tree traversal. When we are working with trees, we may often want to visit all the nodes in the tree. Now, tree is not a linear data structure like array or linked list. In a linear data structure, there would be a logical start and a logical end. So we can start with a pointer at one of the ends and keep moving it towards the other end. For a linear data structure like linked list, for each node or element, we would have only one next element. But tree is not a linear data structure. I have drawn a binary tree here. Data type is character this time. I filled in these characters in the nodes. Now for a tree, at any time, if we are pointing to a particular node, then we can have more than one possible directions. We can have more than one possible next nodes. In this binary tree, for example, if we will start with a pointer at root node, then we have two possible directions. From F, we can either go left to D or we can go right to J. And of course, if we will go in one direction, then we will somehow have to come back and go into the other direction later. So tree traversal is not so straightforward, and what we are going to discuss in this lesson is algorithms for tree traversal. Tree traversal can formally be defined as the process of visiting each node in the tree exactly once in some order. And by visiting a node, we mean reading or processing data in the node. For us in this lesson, visit will mean printing the data in the node. Based on the order in which nodes are visited, tree traversal algorithms can broadly be classified into two categories. We can either go breadth first or we can go depth first. Breadth first traversal and depth first traversal are general techniques to traverse or search a graph. Graph is a data structure, and we have not talked about graph so far in this series. We will discuss graph in later lessons. For now, just know that tree is only a special kind of graph. And in this lesson, we are going to discuss breadth first and depth first traversal in context of trees. In a tree, in breadth first approach, we would visit all the nodes at same depth or level before visiting the nodes at next level. In this binary tree that I'm showing here, this node with value f, which is the root node, is at level 0. I'm writing L0 here for level 0. Depth of a node is defined as number of edges in path from root to that node. A root node would have depth 0. These two nodes D and J are at depth 1, so we can say that these nodes are at level 1. Now these 4 nodes are at level 2, these 3 nodes are at level 3, and finally this node with value h is at level 4. So what we can do in breadth first approach is that we can start at level 0. We would have only one node at level 0, the root node. So we can visit the root node. I'll write the value in the node as I'm visiting it. Now level 0 is done. Now I can go to level 1 and visit the nodes from left to right. So after F, we would visit D, and then we would visit J. And now we are done with level 1. So we can go to level 2. We will go like B, then E, then G, and then K. And now we can go to level 3, A, C, and I, and finally I can go to level 4. This kind of breadth first traversal in case of trees is called level order traversal. And we will discuss how we can do this programmatically in some time. But this is the order in which we would visit the nodes. We would go level by level from left to right. In breadth first approach, for any node, we visit all its children before visiting any of its grandchildren. In this tree, first we are visiting F, and then we are visiting D, and then we are not going to any child of D like B or E along the depth. Next we are going to J. But in depth first approach, if we would go to a child, we would complete the whole subtree of the child before going to the next child.
Chưa đầy 30 giây khi mà các bạn sử dụng con AI này để tạo ra một cái kịch bản video quảng cáo giới thiệu sản phẩm và dịch vụ của bạn. Và bây giờ
in this example tree here, from F, the root node, if we are going left to D, then we should visit all the nodes in this left subtree. That is, we should finish this left subtree in its complete depth. Or in other words, we should finish all the grandchildren of F along this path before going to right child of F, J. And once again, when we will go to J, we will visit all the grandchildren along this path. So basically, we will visit the complete right subtree. In depth first approach, the relative order of visiting the left subtree, the right subtree, and the root node can be different. For example, we can first visit the right subtree, and then the root, and then the left subtree. Or we can do something like we can first visit the root, and then the left subtree, and then the right subtree. So the relative order can be different, but the core idea in depth first strategy is that visiting a child is visiting the complete subtree in that path. And remember, visiting a node is reading, processing, or printing the data in that node based on the relative order of left subtree, right subtree, and the root. There are 3 popular depth first strategies. One way is that we can first visit the root node, then the left subtree, and then the right subtree. Left and right subtrees will be visited recursively in same manner. Such a traversal is called pre-order traversal. Another way is that we can first visit the left subtree, then the root, and then the right subtree. Such a traversal is called in-order traversal. And if root is visited after left and right subtrees, then such a traversal is called post-order traversal. In total, there are 6 possible permutations for left, right, and root, but conventionally, a left subtree is always visited before the right subtree. So these are the 3 strategies that we use. Only the position of root is changing here. If it's before left and right, then it's pre-order. If it's in between, it's in order. And if it's after left and right subtrees, then it's post-order. There is an easy way to remember these three depth-first algorithms. If we can denote visiting a node or reading the data in that node with letter D going to the left subtree as L and going to the right subtree as R. So if we can say D for data, L for left, and R for right, then in pre-order for each node we will go DLR. First we will read the data in that node, then we will go left, and once the left subtree is done we will go right. In order traversal, first we will finish the left subtree, then we will read the data in current node, and then we will go right. In post order, for each node first we will go left, once left subtree is done we will go right, and then we will read the data in current node. So pre-order is data left right, in order is left data right, and post order is left right and then data. Pre-order, in order, and post order are really easy and intuitive to implement using recursion, but we will discuss implementation later. Let's now see what will be the pre-order, in order, and post order traversal for this tree that I've drawn here. Let's first see what will be the pre-order traversal for this binary tree. We need to start at root node, and for each node we first need to read the data, or in other words visit that node. In fact, instead of DLR we could have said VLR here, V for visit. We can use any of these assumptions, V for visit or D for data. I will go with DLR here. So let's start at the root. For each node we first need to read the data. I'm writing F here, the data that I just read. And now I need to go left and finish the complete left subtree. And once all the nodes in the left subtree are visited, then only I can go to the right subtree. The problem here is actually getting reduced in a self-similar or recursive manner. Now we need to focus on this left subtree. Now we are at D, root of this left subtree of F. Once again, for this node we will first read the data, and now we can go left. We will go towards E only when these three nodes A, B, and C will be done. Now we are focusing on this subtree comprising of these three nodes. Now we are at B, we can read the data, and now we can go left to A. There is nothing in left of A, so we can say that for A, left subtree is done, and there is nothing in right as well, so we can say right is also done. Now for B, left subtree is done, so we can go right to C, and left and right of C are null. And now for D, left subtree is done, so we can go right. Once again for E, left and right are null. And now at this stage for F, complete left subtree is visited, so we can go right. Now we need to go left of J, and there is nothing in left of G, so we can go right. And now we can go left of I. For H there is nothing in left and right. Now at this stage left subtree of I is done and right subtree is null. And now we can go back to J. The left subtree for J is done, so we can go to its right subtree. Finally we have K here, and we are done with all the nodes. This is how we can perform a pre-order traversal manually. Actual implementation would be a simple recursion, and we will discuss it later. Let's now see what will be the in-order traversal for this binary tree. In order traversal, we will first finish visiting the left subtree, then visit the current node, and then go right. Once again we will start at the root, and we will for D. Now for A there is nothing in left data is done. For C once again there is nothing in left, so we're done, so we can visit it, read the data here. Now we can go to its right. To E, for E once again left and right are null. At this stage left subtree of F is done, so we can read the data, and now we can go to right of F. If we will go on like this, this finally will be my in-order traversal. This tree that I'm showing here is actually a binary search tree. For each node, the value of nodes in left is lesser and the value of nodes in right is greater. So if we are printing in this order, left subtree and then the current node and then the right subtree, then we would get a sorted list. In-order traversal of a binary search tree would give you a sorted list. Okay, now you should be able to figure out the post-order traversal. This is what we will get for post-order traversal. I leave it for you to see whether this is correct or not. I'll stop here now. In next lesson, we will discuss implementation of these tree traversal algorithms. Thanks for watching.
Should you say really, really, or very, very?
In this lesson, we are going to write code for level order traversal of a binary tree. As we had discussed in our previous lesson, in level order traversal, we visit all nodes at a particular depth. In our previous lesson, we talked about in the tree before visiting the nodes at next deeper level for this binary tree that I'm showing. And now we are done with level 0, so we can go to level 1 from F to level 2. Now it can be and named to go from F to D using this pointer because there is a link. So I can go left to D, but from D I cannot from F because there is no discovered node whose address is known to us but we have not visited. To me, address of the root node, the nodes as well, the root node, and by storing a node in the queue, I'll mean storing the address of the node in the queue. Queue has some discovered node, at least one discovered node, that is as long as the queue is not empty, we can take out. And now I'll enqueue the children of this root node. First I'll enqueue the left child and then the right child. I'll mark visited node in another color. Once again, we are not losing ref because Q is a asserted field and enqueue its children. So we will go on like this until all the nodes are visited. Will go. We are done with our traversal. So this approach character this time because here this is how I'm defining node for my binary tree. I have a structure here with 3 fields, one to store data, and the data type is character this time because in the example tree that we were showing earlier, data type was character, and we have 2 more fields that are pointers to node, one to store the to write a function as argument and print the data in the nodes in level order. Now to test this function, I'll have to write a lot of code to create and install that code. Write is the of one call. We can simply return. Else, if the tree is not empty, we need to create a queue. I'm not going to write my own implementation of queue here. In C++, we can use the queue in standard template library. And to use it, first we'll have to write a statement like hash include queue here. And now I can create a queue of any type. In this function, I'll create a queue of pointer to node with a statement like this. Now, as we had discussed earlier, initially we start with one discovered node in the queue. The only node known to us initially is the root node. With this statement queue.push root, I have inserted the address of root node in the queue. And now I'll run this while loop for which the condition is that the queue should not be empty. And what I really mean here is that while there is at least one discovered node, we should go inside the loop, and inside the loop we should take out a node from the front. This function front returns the element at front of the queue, and because the data type is pointer to node, I'm collecting the return of this function in this pointer to node named current. Now I can visit this node being pointed by current, and by visiting we mean reading the data in that node. I'll simply print the data, and now we want to push the addresses of children of this node into the queue. So I'll say that if the left child is not null, insert it into the queue, and similarly if right child is not null, push it into the queue, or rather push its address into the queue. And I'll write one more statement to remove the element from front of the queue. With call to front, the element is not removed from the queue. With this call pop, we are removing the element.
Step into Wix Studio and handle every part of your build from one platform.
Okay, so this is implementation of level order traversal in C++. You can check the description of this video for a link to source code, and there you can also find all the extra code to test this function. Let's now talk about time and space complexity of level order traversal. If there are n nodes in the tree, and in this algorithm visit to a node is reading that to a node, so time taken will complexity is big O of n. For all cases, irrespective of the shape of the tree, time complexity of level order traversal will be big O of n. Now let's talk about space complexity. Space complexity, as we know, is the measure. We are not using that will grow and shrink while executing this memory used. A couple of cases and used will be, we will have taken out from the queue upon. But for a tree like this, the amount of extra memory use are full. The nodes in two nodes, at least n number of nodes. But for average case, space complexity will be in terms of space complexity. Time complexity will be big O of n for all cases. So in our previous lesson, we talked about level order traversal of binary tree, which is basically breadth first traversal. Now in this lesson, we are going to discuss these three depth first algorithms: pre-order, in-order, and post-order. I have drawn a binary tree here. Data type filled in the nodes is character. Now as we had discussed in earlier lessons, in depth first traversal of binary tree, if we go in one direction, then we visit all the nodes in that direction. Or in other words, we visit the complete subtree in that direction, and then only we go in other direction. In this example tree that I've drawn here, if I'm at root and I'm going left, then I'll visit all the nodes in this left subtree, and then only I can go right. And once again, when I'll go right, I'll visit all the nodes in this right subtree. If you can see, in this approach, we are reducing the problem in a self-similar or recursive manner. We can say that in total, visiting all the nodes in the tree is visiting the root node, visiting the left subtree, and visiting the right subtree. Remember, by visiting a node, we mean reading or processing the data in that node, and by visiting a subtree, we mean visiting all the nodes in the subtree. In depth first strategy, relative order of visiting the left subtree, right subtree, and the root can be different. For example, we can first visit the right subtree, then the root, and then the left subtree. Or we can first visit the root and then the left subtree and then the right subtree. Conventionally, left subtree is always visited before right subtree. With this constraint, we will have three permutations. We can first visit the root and then the left subtree and then the right subtree. And such a traversal will be called pre-order traversal. Or we can first visit the left subtree, then the root, and then the right subtree, and such a traversal will be called in-order traversal. And we can also go left, right, and then root, and such a traversal will be called post-order traversal. Left and right subtrees will be visited recursively in same manner as the original tree. So in pre-order, once again for the subtrees, we will go root, left, and then right. In order, we'll keep going left, root, and then right. The actual implementation of these algorithms is really easy and intuitive. Let's first see code for pre-order traversal. I've first written the algorithm in words here. In pre-order traversal, we first need to visit the root, then the left subtree, and then the right subtree. Now I want to write a function that should take pointer or reference to root node as argument and print data in all the nodes in pre-order. Let's say visiting a node for us is printing the data in that node. In C or C++, my method signature will look something like this. This function will take address of the root node as argument. Argument type is pointer to node. I'll define node as a structure with three fields like this. Data type in this definition is character, and there are two fields to store the addresses of left and right children. Now in pre-order function, I'll first visit or print the data in root node, and now I'll make a recursive call to visit the left subtree. I have made a recursive call here, and to this call I'm passing address of the left child of my current root, because left child will be the root of left subtree. And I'll have another call like this to visit the right subtree. There is one more thing that we need to add in this function and we will be done. We cannot go into recursion infinitely. We need to have a base condition where we should exit. If a tree or subtree is empty, or in other words, for any call if root is null, we can return or exit. Now with this much of code, I'm done with my pre-order function. This will work fine in C or C++. Actually, in C, make sure you write struct space node instead of writing just node. The rest of the things are fine. It will be good to visualize this recursion. So let's now quickly see how this pre-order function will work if this example tree that I'm showing in right here is passed to it. I'll redraw this tree and show it like this. Here I'm depicting node as a structure with 3 fields. Let's say the leftmost cell here is to store the address of left child, the cell in middle is to store the data, and the rightmost cell is to store the address of right child.
Understanding data structures and algorithms is difficult. Don't worry, Log2Base2 can help you. With our animation videos, you can start visualizing the...
Now let's assume some addresses for these nodes. Let's say the root node is at address 200, and I'll assume some random addresses for other nodes as well. And now I can fill in left and right fields for each node. And as we know, the identity of tree that we always keep with us is reference or address of the root node. This is what we pass to all the functions. In our implementation, we often use a variable of type pointer to node named root to store the address of root node. We can name this variable anything. We can name this variable root, or we can name this variable root ptr, but this is just a pointer. This particular block that I'm showing here is for pointer to node, and all these rectangles with 3 cells are nodes. This is how things are organized in memory. Now for this tree, let's say we are making a call to this pre-order function. I'll make a call to pre-order, passing it address 200. For this call, root is not null, so we will not return at first line in this function. We will go ahead and print the data in this node at address 200. I'll write output for all print statements here. And now this function will make a recursive call. Execution of this particular function call will pause. It will resume only after this recursive call, pre-order 150, finishes. This second call is to visit this left subtree. This call pre-order 150 is to visit this left subtree. Address of the left child of node at 200 is 150. Once again, for this call, root is not null, so we will go ahead and print the data. Data in node at 150 is D, and now once again there will be a recursive call. With this call, pre-order 400, we are saying that we are going to visit this subtree. Once again, we will print the data and make another recursive call. Now we have made a call to visit this particular subtree with just one node. For this call, we will print the data, and now for node at 250, address of left child is 0 or null. We will make a call, pre-order 0, but for this call we will simply return because the address in this variable root will be null. We have hit the base condition for our recursion. Call to pre-order 0 will finish and pre-order 250 will resume. Now in this particular function call, we'll make another call for right subtree. For node at 250, even the right child is null. We will have another recursive call passing address 0, but this once again will simply return. And now call to pre-order 250 will finish and call to pre-order 400 will resume. Now in call to pre-order 400, we will make another recursive call to pre-order 180. With this call pre-order 180, we are visiting this particular subtree with just one node. For this call, first we will print the data and then we will make a recursive call to pre-order 0. Now pre-order 0 will simply return, and then we will have another call to pre-order 0 for right child of 180. The recursion will go on like this. There is one thing that I want to talk about here that's happening in this whole process. Even though we are not using any extra memory explicitly in our function, because of the recursion, we are growing the function call stack. We have discussed memory management a number of times in our earlier lessons. You can check description of this video for a link to one of those lessons. As we know, for each function call, we allocate some amount of memory in what we call stack section of applications memory. And this allocated memory is reclaimed when the function call finishes. At this stage of execution of my recursion for this example, my call stack will look something like this. I'm writing P as shortcut for pre-order because I'm short of space here. Let's say we made a call to pre-order passing it address 200 from main function. Main function will be at bottom of stack. At any time, only the call at top of stack will be executing and all other calls will be paused. call stack keeps growing and shrinking during execution of a program because memory is allocated for a new function call and it's reclaimed when a function call finishes. So even though we are not using any extra memory explicitly here, we are using memory implicitly in the call stack. So space complexity, which is measure of rate of growth of extra memory used with input, will depend upon the maximum amount of extra memory used in the call stack. I'll talk about space complexity once more later. For now, let's come back to this recursion that I was executing. Call to this pre-order 0 will finish and pre-order 180 will resume. Memory allocated for execution of pre-order 0 will be reclaimed. Now for pre-order 180, both recursive calls have finished. So this guy will also finish. Even for pre-order 400, both calls have finished. So pre-order 150 will resume. Now this guy will make a recursive call to pre-order function passing it address 450, address of its right child. Memory in the stack will be allocated for execution of pre-order 450. Now in this call we will first print the data and then we will make two recursive calls to pre-order passing address 0 each time because for this node at 450 both children are null. Both calls will simply return and then if you can see the call stack will grow only to n or height of the tree of h, where h is height of the tree. Okay, coming back to the recursion, we are done with pre-order 150, so pre-order 200 will resume. And now we will make a call to visit this particular subtree. In this call, we will print j, and then we will make a call passing address 60. So now we are visiting this particular subtree. Here we will first print g, and then this guy will make a call to pre-order 0. Which will simply return, and then there will be another call to pre-order 500. Here we will print I, and then we will make two recursive calls passing address 0 every time because node at 500 is a leaf node with no children. After this guy finishes, pre-order 60 will resume. Now this guy will also finish and pre-order 350 will resume, and now we will have a call to pre-order 700, which once again is a leaf node. So k, which is data in this node, will be printed, and then we will make two calls passing address 0, which will simply return. Now at this stage all these calls can finish. We are done visiting all the nodes. Finally we will return back to the caller of pre-order 200, which probably would be the main function. So this is pre-order and post-order. Same call and on here will be this. This particular binary search tree would give us elements in the tree in sorted order. Okay, let's now write code for post order. For this function, once again, the base case will be the same. I first need to tree, so I'll have this another for this example for you. You can check the description of this video for a link to all the source code. Let's now quickly talk about time and space complexity of these algorithms. Time complexity of all these three algorithms is big O of n. If you could see, then there was one function call corresponding to each node where we were actually visiting that node, where we were actually printing the data in that node. So running time should actually be proportional to number of nodes. There is a better formal and mathematical way of proving that time complexity of these algorithms is big O of n. You can check the description of this video for a link to that. Space complexity, as we had discussed earlier, will be big O of h, where h is height of the tree. Height of a tree in worst case will be n minus 1. So in worst case, space complexity of these algorithms can be big O of n. In best or average case, height of a tree will be big O of log n to the base 2. So we can say that in best or average case, space complexity will be big O of log n. I'll stop here now. In coming lessons, we will solve some problems on binary tree. Thanks for watching.
It's divide and conquer. We want to reduce the size of the search area by half each time in order to find a target number. This is where that condition comes into play, though. We can only leverage the power of eliminating half of the elements without even looking at them if the array is sorted. If it's a complete mix-up, we can't just out of hand discard half of the elements because we don't know what we're discarding.
All right, team, we're transitioning to FLAC, but tasks are still going to be on Bullfrog.
Did nobody see my poppycock post?
What we can do is, as we